I'll take over.
Starting.
All right. Thank you so much, Safka, and the organization for inviting me to present this webinar. It's a pleasure to be here. My name is Gisela Viegas. I'm a seismologist. I work for Newmont, a mining company, at the corporate office. I've been with initially Newcrest and now Newmont for 7 years now. In terms of my career, I started studying geophysics at uni, and then I went to do a PhD in seismology. At the time, my interest was intraplate earthquakes. And then from there, and also ground motion modeling. And then after that, I worked as a postdoc at Lawrence Berkeley Lab to start working into induced seismicity in geothermal environments then. And then after that, I went to Canada, where I worked as a consultant for a seismic monitoring company. We did a lot of work monitoring for oil and gas, but also mining, where I stayed for about 8 years. And then I went to Newmont, and I've been working mostly across all mine sites. For deep underground mines, of course, they're seismically active, so I support the sites on that aspect and the company. But also, I also work for open pit mines in terms of regional seismic hazard assessment and other problems related to seismicity that arise. All right, so let's start. The title of the presentation is Discrimination Rock Failure Processes in Hard Rock Caving Mines Using Seismic Moment Tensors. So I chose this topic. Let's see how I go to the next page. Okay. Wait. Just give me a second because I'm having some problem. Okay, here we go. Next one. Okay. So I chose this topic because I work closely together with a lot of geotechs at Newmont, and I understand that there's not a good understanding in terms of what is moment tensors and what you can take out of it. There's a lot of nice presentations and webinars on moment tensors done by seismologists for seismologists, but it's the degree of complexity is a bit high for non-seismologists. So I decided to just try to simplify it and just explain what you actually, when you look at the moment tensor, what you should take out of it, the basic information, and how I use it when I look at seismicity at the mines, and also what other byproducts you can take from it. So this is the basis of this webinar. Apologies to my fellow seismologists. This might not be as interesting as they expected, but I think there's value to it. And also, I just added a disclaimer that the views and interpretations are my own and do not reflect Newmont positions or are endorsed by Newmont. All right, so what is a moment tensor? Moment tensor is a mathematical description of the forces that drive earthquake rupture. It's a symmetric second rank tensor and has moment of force couples. So basically, it describes the failure mechanism of seismic rocks. So here on the side, we have a schematic of the moment tensor. So moment, we know it's force times displacement. And capital M is for moment, and then 1 and 2 are the axis. So we have a force couple applied in axis 1, and then we have displacement, in this case, also along axis 1. So the second one here, M12, we have the force couple also applied in axis 1, but then the displacement is in axis 2, and on and on. So basically, that's how we describe the geometry of the failure mechanism of our seismic sources. So why is this useful? In broad sense, for the mathematical expression of the displacement field, with what we actually measure with the instruments is the displacement field or the velocity field. So it can be expressed as the moment tensor times the Green's function that describes the impulse, the medium response to the force impulse, and convolved with the source time function. So if we assume the Green's function, we think we know the medium, then we can solve for the moment tensor and the source time function based on what is the displacement field that is measured. So it's a very brief description. So what do we actually see when we look at a beach ball or a focal mechanism representation? Because we've all seen these on maps and stuff. So usually we can see it in 3D, like a full sphere, or we can see it in a map, just like a circle with some lobes of dark and light colors. So basically, the beach ball represents the radiation pattern of the P waves, the compressional waves. So if we assume the source is in the middle of this is called the focal sphere. The dark areas are the areas where the initial movement is compression. So you have material coming out, moving out of the focal sphere, and the light colors, or usually white, means dilation. So we have material going into the focal sphere, which is a simple way of looking at it. So usually if you work in a mining site and you have the 3D volume of your mine, you see these beach balls in 3D. But sometimes when you look at a map or a representation, you see it in 2D, which is just a circle. So this is the lower hemisphere projection that I put here some examples. So you have two conjugate faults because it's a mathematical description, they both can be correct, either can be correct. We don't know how to differentiate them just by the moment tensor solution. We'll need some physical properties to do that, and I'll talk about that next. So you'd have one fault plane here, which is this one here. I don't know if you can see my mouse working, and the other one here, which is the other one here. So in this case, you'd have compression on this direction, so you see it here, and dilation on the other one, which is in the middle. So here's a schematic. Oh, and also the pressure axis is in the middle of the dilation lobe, and the tensional axis is in the middle of the compression between the two planes. And then there's the null axis. So if you look in terms of block motion, so here we see again the lower hemisphere, and we have outward motion in the darker area and inward motion in the lighter area. And this is what you see for a strike slip mechanism, and you can either have right lateral motion or on this direction or in the other direction. So on this one, on that one. Of course, if you have, there's a structure there that has this orientation, then you can discriminate which one it is. Similar for the normal faulting, where you have the hanging wall descending, then you'd have the middle part is white and the compressional lobes are on the sides, which is the example I gave here on the left. Then the reverse fault, it's the opposite. So you have the hanging wall riding above the lower wall, the footwall. And then there's sometimes the geometry is not this simple. There's actually some rotation, and you can have some oblique reverse. For example, in this case, you have reverse, but it's also a bit side to side. So the representation will be kind of a rotated. You don't have the two nodes, focal plane nodes here on the sides, but they actually rotated. So yeah, when you look at this now, this is lower hemisphere and it's a darker area, so compression motion outwards of the focal sphere. So there's not all of them are shear. There's actually different types of sources that are represented by moment tensors, depending on the failure mechanism. So here are some examples of them. You have explosion or implosions, where you have isotropic motion in all directions. So either you have everything dark or everything light, depending if it's explosion will be every compression in all directions and implosion the other way. So there's a example here of the explosion and what the moment tensor beach looks like. There's dilation modes, which is a mixed mode. So you have some openings, which will look something like this if you see it represented. There's the compensated linear vector dipole. It's a mouthful, but it's basically you have change in geometry of the source, but there's no change in the volume. So you can see it if you have a little block of putty and you squish it and it goes to the side. So the total volume is the same. It's just the geometry that changed. Or on the other side, you can push it upwards and down and it will come into it will narrow. So this one here, example here is the squishing from above. So you press it in the middle and it goes out on the sides. Double couple is the one we discussed, that it's mostly shear slip on structures, and it depends on the orientation. You can see the 4 quadrants well delineated, or if it's just deep slip, you'd see it's just half of the beach ball. So these are the main modes, and there's a source type plot, very used, which is the Hudson plot, that tries to represent all these type of sources in one plot visually. And the way you can look at it is in the vertical axis gives you change in volume of the source. So explosions is the end members are explosions on the top and implosions in the bottom. Explosions, you have the source getting larger in all directions, and implosion also material goes into the source, so you have getting smaller in all directions. So that's the vertical axis. And then the horizontal axis would be the CLVD. So there's no change in volume, but there's a change in geometry here. The shear or the double couple is set in the middle because there's no change in volume or geometry. It's just shearing on the plane. And then everything in between will be plotted in different in the other areas of the Hudson plot. In mining, we see a lot of events plotting in this area here, the tensile closing crack or the dipole, and I'll talk about these in the next slides as well. For example, in hydraulic fracturing, we also see a lot of tensile shear openings on this end here and closures on this one. One more thing, usually when you solve for the full moment tensor, you can have any of these mechanisms, and usually to be able to better interpret it's decomposed into the 3 dominant components, which is the double couple, the CLVD, and the isotropic. So explosion, CLVD, double couple. And there's different schemes or mathematical options how to decompose them. Just pick one and keep using that one. All right. So in terms of the seismic source mechanisms in cave mines, there's quite a variability, but I like to group them into 2 main families, which is the slip type and the crush type. I think this first heard this crush type grouping name from Dima Malovichko, and we've adopted since then. I think mines, at least our mines, Newmont mines, are using it more frequently because it does a good job describing the type of failure. So the slip type is the same as tectonic events. It's just shear on on a structure, usually a fault, but could be a dike or something else. So it's shear slip. It's away from, so it's high confinement. So there's no option for the rock mass to expand into voids, because it's not usually close to voids in terms of relative to the size of the failure. And in the terms of moment tensor, in terms of the composition, theoretically it will have 0 isotropic, 0 CLVD, and 100% double couple. So it will plot here in the middle of the Hudson plot. In terms of damage to the mines, the shear type events don't directly breach ground support, but it can include dynamic shaking, and it can make rock fall from the shaking. So there could be derived damage from such events if they're large enough, if the dynamic loading is large enough. So the other family is the crush type, and Dima Malovic came with a really nice model to understand the crush type, which I'll try to explain here. You can go to his paper if you want to look into more detail, but it basically represents the loading. It's a stress fracturing and sudden inelastic deformation. So you have usually for pillars and rock mass under high stress load that suddenly fracture, and there's material that comes into the opening. Could be bulking or could even be a rock burst, so material loose and coming in. But so if you have loading in this example from horizontal loading, then you'll have bulking from the vertical, but it could be rotated, depends on the stress field at the site. So you have material coming from the side, in this case, in this example here. But the interesting thing is that because you also have convergence of the side walls, the seismic signal that you record is the bulking and also the convergence. And the convergence tends to be a longer wavelength. So it's a dominant signal. So actually, when you look at the moment tensor, you just see like it looks like an implosion beach ball, but it does plot in the Hudson plot close to the shear tensile closure in the dipole here in this area. In terms of the decomposition, you have a high component of isotropic implosion that's from the convergence inside the void. And then you have a large component of CLVD also from the squishing of material coming from above in this example here. Theoretically, you should not have a double couple. In reality, we always see some small percentage of double couple. So this has a big impact because this is self-initiated and just from high stress in pillars and close to excavations. All right, so I already spoke about the slip type and the crush type. Here I'm just showing examples where the double couple force is and the representation in terms of the moment tensor that you see. But there's also blasts, as I mentioned. And we also see single force mechanisms, so it's not a double couple, so it cannot be represented here in the Hudson plot. And you usually see this type of events in raise bores and caving events, and I'll show one example of each. Other signals that mines are very noisy, seismically noisy, and there's other signals that we also see that I'm not discussing here because they're noise signals from the crusher chamber. It's very low frequency, often quite noisy. There's drilling going on, so you have those high frequency signals from the drills. There's material being dumped into our passes, and it hits the walls and the floor, so we pick those up as well. And there's secondary breaking of rocks already in the drop points. So these are classified, and and not analyzed. There's a classification when the monitoring is done, and they're classified according to the type of signal. We also see tremor, which is basically S waves, but not focusing on that. So, okay, changing gears a little bit now and looking at what do sensors actually record. So this is from Stein and my session. And this is an example from an earthquake, but it's basically the same thing. In this case, you have the surface of the Earth here and the earthquake occurring at some depth, and the sensors are at the surface. In underground mines, the sensors are underground, not at the surface, but everything else holds. So we have an event that releases seismic waves that propagate towards the medium. So the signal that we're picking up is the source signal first, then the structure, which is what happens to the ray paths as they travel to the medium. They can be refracted, reflected, they bend, they can focus, depending on the structure that they go through. And then they're recorded by the sensor, the instrument that also has a response. There's not a flat response depending on the frequencies. At some frequencies might amplify or de-amplify the signal. So at the end, the seismogram is the convolution of all these time signals, the signals in the time domain. And as the saying goes, if you put garbage in, you get garbage out. The meaning of this is when you're looking into seismic signals for location or moment tensor inversion. Just to give you another visual example, if your event occurs here and it has a certain mechanism, and you have an array, or in this case an array, but it could be just individual sensors around, the ray path is going to be straight lines between the event and the sensors, and you'll see a nice waveforms from the P arrivals from the top sensor to the bottom here, and then the S arrivals. But this is the ideal case, but actually in mines, there's lots of voids. So if you put a void in the middle of the ray path, what's going to happen is that the ray is going to bend around they try to go to the high velocity medium, so they tend to bend around the voids. If there's some material in it, they can also propagate through the void at a slower velocity and kind of losing a lot of high frequency content. So, and there will be also reflected phases and refracted phases coming from the void boundaries. If there's often also we see shear splitting, so the S waves split into a fast S wave and a slow S wave, depending on the orientation of the cracks around the voids. So there's a lot of effects that affect the wave propagation when we don't have a nice, competent rock mass that the ray paths travel to. And so this to say that if in our models, to calculate the event locations and to calculate moment tensors, if we don't consider those distortions to the ray, which we usually don't, because we usually just tend to use the simplest models, then whatever it's not, it's from the structural model, the ray path, and it's not considered, it's dumped into the source. So it will generate artifacts or incorrect solutions for the source just because we don't have the right model description that the waves go through, the ray paths go through. So things to aim when you're designing a seismic system in a mine to acquire data is, first of all, for moment tensor inversion specifically, there's some main points, simple ones. One is getting good focal coverage. So you want to sample the whole focus sphere. You don't want to sample just a portion of it, because although there's some symmetry, you need the whole focus sphere to get a good solution of the moment tensor. Because if you're just seeing parts of it, there could be several solutions that might satisfy the observations, and you won't know which one is the correct one. You want to try to get simple ray paths. So again, don't put sensors on the other side of the ore body or the excavations. Try to have ray paths that go to undisturbed competent rock mass, if you can, if it's possible. Make sure you have adequate velocity model, attenuation as well, so you can have good locations of your event. So if the location is very far off, then that will also affect the moment tensor solution that you get. Another important thing is to get the sensors properly oriented. So you need to know the direction that the sensor axes are at, so then you can do rotations and inversions accurately. And then be mindful to keep sensors away from persistent noise sources like crushers. So you don't want to put a sensor close to a crusher because it's very noisy and it will elevate your noise floor, and it will make more difficult to see the arriving phases, or also close to a decline where there's trucks going all the time, that type of thing. So these are like the main points for when you're designing an acquisition system. I also heard people saying, "Oh, but how do I know that the moment tensor solution is accurate?" Sometimes if it has a lot of CLVD, it's just garbage, or how can I trust the solution? Well, there's metrics about the inversion and the geometry of the acquisition system relative to the focal sphere. And the consultants usually provide, no, not usually, they always provide metrics and thresholds that they can accept a solution. Traditionally, it's automatic. If it's below the threshold, it's not accepted. But they also give us that information. We just need to know where to look. So I would suggest ask your seismic monitoring consultant and ask them what metrics do they use and how to use them. It varies, so I'm not including them here. Also, to add that moment tensor solutions just for a point source. This is assuming point source. We're assuming the event is one point. It occurs. It's a small point relative to the distances that we're considering. And sometimes for larger events, that's not adequate, or complex sources that you have different mechanisms, spatially varying. So in these cases, it's better to do a finite source inversion, and each finite subsources can have its own moment tensor. And as I mentioned before, single force events are not also represented by moment tensors. So an option is the option that the consultant that we work with, the seismic management company we work with, they solve for both, and the one that gives better results that fit better the data, they choose that one. All right, so types of seismic failure in caving mines. I was inspired by the World Cup to make this slide. I thought it was appropriate. So just to give you some examples of source mechanisms from a cave mine, in this case is Cadia East in Australia, in New South Wales. Cadia East is a panel caving mine, currently Just give me a second. So it started with Ridgeway. It started with an open pit, then the Ridgeway, which is now shut down, and the current mine in operation is KDA East. So we have panel PC1 here. This we call this PC2 panel, and now PC23 is being developed, and PC12 as well. So this is 2 years ago. So I'll show some examples of seismic source mechanisms and moment tensors that we got at KDA East. For the non-mining people, just a quick explanation: what is a block panel caving? What's the block caving mine process? So it starts by developing the footprint and where the extraction level is. So at depth, you go down and you develop the extraction level, and then you start mining. And gravity aids in the mining. So as you start, you blast initially, and then rock starts breaking and falling down. And then the cave propagates. There's a stage of cave propagates upwards until it reaches the surface. And then there's a phase of steady state production where you're just mining. So one of the sleep type events that we see on KDA East is sleep on geological structures. These are structures that are outside of the ore body. So here in the middle, we have in the cave. And then we see some events, sleep type events occurring outside of the cave. And from the moment tensors, it's a bit hard to see, but you can see that they align along one of the fault planes spatially and also in terms of the moment tensors. So when you see a bunch of moment tensors and we can rotate and the location aligns and the fault plane solution aligns, we can identify that we have structures. So these are 2 examples of 2 structures that are active or were active. Another sleep type events that we see. So in this one, the structures were pre-existing. They were here and they started to be activated as we mine, and the stress field changes and they start having some activity in them. In this case is different. These are not pre-existing structures. These are called Ortlepp shears. So they're new fractures generated by higher shear stresses. So there's an example here. The stress field tends to wrap around the excavations, the voids, as it shows here on the left. Sorry. And here in the bottom, you see that it bends and it's really high stress. And what we see at Cadia at some points was that some small fractures were generated and they were defining a plane that didn't correspond to any existing structures. We also see Ortlepp shears, but in this case, very small magnitudes -2, -3, very small ones inside the pillars in the development area. So some examples here of the beach walls and the pressure compression axis and the 2 fault planes. What tends to happen, these are very small, and because there's voids, so these are the drives here, and because there's voids, the stress is concentrated in the pillars, and you start having these very small shear fractures, and they tend to be oriented parallel to the drives, to the voids, to the tunnels, and sometimes they go around. So this is an interesting observation. And for example, for Cadia, when we started developing PC23, so this is PC23, it started in this corner and went here. This is an example of the stress field. As you start developing the drawbells where you're going to extract the ore, the stress abutment of the cave starts being pushed forward. So this is high stress areas in these pillars. So you do the development first and then the drawbells. And so we see these small outlet shears moving in time and following the abutment stress over time. Moving on to crush type events. Not sure I'm on time. Oh, okay, I need to rush a little bit. All right, crush type events, we see a few, and you can see here they're like the white focal mechanisms. They're usually small magnitude in this case. We see them on raised bores, which are these vertical structures. We see as we're developing the drives, sometimes in some higher stress areas, you see some popping up, some small events along the drive because it's low confinement. And also we see them in the cave as the yielding area extends outward. You also see these type of crush type events in the cave. A little bit in more detail, the crush type events along the drives, they tend to locate close to the drives. And you can see that the pressure axis and tension pressure axis tend to bend around the drives, and the tension axis tend to be perpendicular to it. For larger events that also occur, especially if you have abutment areas for long periods of time, like areas of high stress, you can have larger events occurring once in a while. So this is an example, and this, in case we got a finite source solution. So each of these subsources are part of the total source. Usually you see, because there's bulking and there's sometimes there's material falling from the ground support. So the total area is the source area. The damage area where you see damage is the source area. So in this case, just showing an example where the failure starts here in the dark blue and propagates radially and in direction to the cave into the red. In terms of blasts, because we have good coverage, very good seismic monitoring system, and we have sensors very close to areas that are being blasted. This is production blasts, so there's a lot of blasts in sequence. We're close enough to actually see the P and S wave before the other blasts comes in. So this is a sequence of blasts in 3 sensors, and here we can see PNS waves very well defined. If we know what the blasting sequence should be, we can plot it on top of the observed, and we can also detect which ones failed. So this one was supposed to be the third blast, third shot didn't happen, and also in this case, the sixth one didn't happen. So it's a good way to monitor that. So in terms of single force events, just adding 2 examples from raised bores. So as I mentioned before, we have crush type events here, but sometimes there's material that falls off the raised bore and hits the bottom, the floor. And then we have a bunch of single force. It's just from the impact of the falling material. It might also bounce, hit the wall, and in this case could be also single force. We also see in some areas of caving events, and I think these are related. We assume these are related with blocks getting loose from the rock, and it could be an elastic rebound because they're pointing upwards of the rock. Once the block gets released, the remaining of the rock bounces up. So that's an interpretation. Some examples that I thought it were interesting to show from other cave mines. This one is a sublevel caving. So this is the open pit. This is the sublevel, but it also has, it's a complex, there's different mining methods in this mine, and it has some reefs here that are stoped in narrow vein, long hole, open stoping. So, and this is the case that I'm going to show, which I thought it was interesting. So here we're looking along the reef, and we see these moment tensors that look like CLVD mostly. So they're light color at the top, and they have dark around it. So it looks like you're squishing, and material, and the source is going outside. And in terms of the moment tensor decomposition, the isotropic component is very small, very large CLVD, and also kind of average double couple. And the interpretation that we do from this one is that either the stope is converging or there's a pillar failure. So the pillar fails and material bulks to the side. But because this is a reef and there's discontinuity boundaries between the ore and the host rock, there's also some shear on the reefs. So I thought so we do have some not negligible double couple component. So I thought this would be an interesting example to show. Another complex mechanism from another mine, also a sublevel caving mine in this case. It's near a void, so it's a dominant crush type mechanism. So we have the sublevels here, and this is the two fault planes that we see that we can resolve. It had also a 23% double couple, so not negligible. And in this case, although dominantly is a crush type, we see that it's structurally controlled because we do see there's a structure that aligns well with what this fault plane here. So it adds complexity. It's not just crush type or sleep type. Sometimes there's a mix. All right. Further uses of moment tensors. As I mentioned, it's good to identify and map geological structures. So once you start developing the caves, and some of these structures are activated by the rotating or adjusted stress field, we can identify new structures. This example is for Cadia. Cadia has a lot of faults, but actually most of them are not seismically active. Most of the activity is in porphyry dikes. And in this case, we observed, in this case called the northern seismic plane and southern, because it's in the north and in the south. These structures were not known. Exploration teams usually are more concerned in making structural models for the ore body, and they don't care that much on the waste rock. But when you establish the cave, the stresses change around it, and so if there are structures there, they might be activated. So it's good to know that they're there, and we usually don't have that information. So when we start seeing that, we can pick them up, and then we can drill to make sure what they are, and make sure we have the correct model, which will have implications for seismic hazards assessment. Also, we see these structures when we do hydraulic preconditioning. This is a case that we were actually targeting a structure that was becoming active, but during that process, we also saw identified other structures. And here in the nodal plane plots, there's the dike A that was the one being targeted, but then we saw a lot of seismicity in the dike B and very little in the C, but a little bit as well to be able to map it. And you can see source type in this case is mostly shear, so call it hydro-shearing type. At KD East, there's a very there's a big hydraulic preconditioning programs before the block cave are developed to aid in the caveability of the block cave, and also to reduce seismic hazard. And in this case, this is all the theoretical model hydraulic fractures that would get for the underground hydraulic preconditioning program. And during this program, we were able to identify some structures where we saw hydro shearing, which are here identified HS. and also H1. And later on, when we started developing, establishing and developing the PC23 cave, some of these planes were reactivated. So it was interesting to see that it was consistent with the early observations. I'm running out of time, so I think I'll just skip this part and I'll revert to the study. That this was a work that we did with a big input from the structural geologists and numerical modeling to identify structures that have high potential to slip, and then use numerical modeling to forecast what, based on the next mining steps, what the maximum potency, seismic potency in this case would be. So yeah, you can go check the details in the paper, but quickly we use the observations for the time period that we had data to calibrate the frictional properties on these structures. And then based on that, we were able to forecast future release of seismic potency. Another byproduct that you can get is do stress inversion. So you can determine the in situ stress from moment tensor solutions. If you have a group of events where you have seismic moment tensors, ideally they need to be different orientations, not the same. And there's a lot of literature on that. But this is just an example from the TP and B axis. You can run in IMS software as this, and I think the other companies also have it. You can just select events, run it yourself, and you'll get the direction of the, it's hard to see here, but of the sigma 1, sigma 2, and sigma 3. And you can get the relative amplitudes between sigma 1, sigma 2, and sigma 3, but not the real amplitude, just the relative amplitudes between the three principal stresses. All right, another thing we use is to verify if the strain models are correct from the numerical models. So in this case, the numerical model, this was for Telfer, I think. So this was a stoping. In between the stopes, you expect the strain axis to, as I mentioned, wrap the pressure axis to wrap around the stopes and the tensional axis to point towards the stopes. The model does that, and then the seismic data is here on the right, and you see the same pattern. So they, yeah, you can tell the model is doing a good job, and it's mimicking the observations. And you can use, based on that, if you want to separate events to look into specific characteristics, you can use, for example, the plunge of the pressure axis to differentiate them, like we did here. So you see different distributions of strain in the modeling and also in the observations. All right, the rock burst hazard assessment tool is a tool that was developed in the last few years, couple of years. It incorporates information from a lot of data sets, rock mass properties in terms of strength, the geometry and timing of excavations, the stress modeling based on planned mining steps, ground support as well, the installed ground support that's put in place, and of course seismic data also uses input into this, we call it RBHA, so rock assessment tool. You can it also includes observations of damage, so you can do back analysis of events. So basically, what is useful in terms of moment tensors, you can discriminate between shear type and crush type. And based on the ground support capacity curves that you put into the program, you can determine from the seismic events how much of it was consumed. So how much the bolts were distended from the seismicity that occurred already. So that allows you to manage ground support and be proactive in terms of reinforcement, and to understand when capacity might be close to the limit, or when the capacity is not enough, or already it's not still enough if you have a larger event that you expect, that you designed for. So maybe proactively you can reinforce those areas. So just an example here, the consumption of ground support in terms of displacement, of how much the bolts have been extended and when's the limit. And it does a statistical approach for that as well. The example here is just mapping in terms of the depth of failure. So if you remember crush type, depth of failure is this darker area, the vertical area. When you have a crush type event, it extends, increases. And as it extends, the bolts are being stretched. So then you can use this to determine, based on the events that occurred in those areas, you can determine how much your capacity is left. There's other inputs that are used from seismic data as well for the duration of the bulking, that it's also important for designing ground support. And then you can do probability of strain bursts, and also input ground motion hazard. So you can estimate based on your seismic hazard models how much peak ground velocity, dynamic peak ground velocity is going to hit your ground support, your structure, your drives, and how much is going to impact in the ground support. All right. That's all. Thank you. I hope this was helpful and you get a little more of seismic moment tensors next time you look at them. I don't know if there's time for questions or